This is Peter with CalcBook. Today we're going to be looking at timber connection design and specifically looking at a bolted connection in lateral loading. So just a quick recap on our connection design, right? We use the National Design Specification, also known as the NDS, and we have the spec and we have the supplement. The spec, right, gives us our design procedure, our capacity equations, adjustment factors. It also gives us parameters and equations for whether we're looking at lateral or withdrawal loading, and then also additional information for our dowel type fasteners, which is what we are going to be using CalcBook for. So we have bolts, lag screws, wood screws, nails and spikes, drift bolts, and drift pins. The supplement, right, that's for your reference design values. We don't use that as much for connection design. That's mostly for member design, but we still can reference it for, different various properties for the members, for our main member and side member and specific gravity and things like that. So we still may need to reference that during the design. So for us today, right, we're going to be looking at lateral loading and we're going to be looking at bolts. So let's go ahead and take a look at our problem statement. Right, we are going to verify the connection design given the following parameters. Right, so we have a single bolt in lateral loading here. Our main member is Douglas fir larch with a thickness of 1.5 inches and an end edge distance of 3 inches. We have a side member, which is also Douglas fir larch, with a thickness of 1.5 inches and an end edge distance of 3 inches. Right, so we basically have two 2x4s bolted together. Our bolt diameter is 5/8 inch, and that's in single shear. We have a dry in-service condition and then a dry fabrication condition. And we're going to be using LRFD analysis for this. And these members are loaded longitudinally, right? So as these boards try to pull apart from each other, they are going to be pushing or bearing towards the end of each board. So as this member tries to go to the left, right, we're bearing internally on the inside surface here, which pushes towards the end of the member, and vice versa on this other one here. And that comes into play into some of the equations when we get into it. We have a loading of 175 pounds dead and 250 pounds live. So let's go ahead and open up CalcBook and we'll get started on the design. All right, we've got CalcBook open now. So we go ahead and click into our Timber NDS 2018 design module. And then we'll click into our connection designs. And we have 4 options here, right? We have our lateral load on a single fastener, our lateral load on a fastener group, our withdrawal load on a single fastener, and then we have combined loading, lateral and withdrawal on a single fastener. So for us, right, we're going to be looking at lateral load on a single fastener. Click continue, get that loaded up. And we can start going through our inputs here. So our dowel type is going to be a hex bolt. We are going to start with a 5/8 diameter bolt and see if that works for us. It is in single shear. And our dowel bending yield strength is going to be 45,000 psi, and that comes from table I1. There's different strengths for different types of fasteners, but for us, for a bolt, we're going to use 45,000. And then we start updating our properties for our main member and our side member. So we start with our main member is wood. It's Douglas fir larch. The load direction is going to be tension, and it's a softwood because of Douglas fir larch, but it's tension because, like we talked about in the intro, the bearing of this bolt is towards the end of the member, and so that is going to be in tension. Our angle is going to be 0 degrees, right, because the fibers of the wood are longitudinal, and so we are parallel with those fibers. Our thickness is going to be 1.5 inches, and our end distance is 3 inches. Then we go to our side member. It's also Douglas fir larch, and our load direction is also tension, and we are 0 degrees. We're parallel with the fibers. And our side member thickness is also 1.5 inches, and our end distance is 3 inches. We have some additional adjustment factors here. Our end grain condition, right? We are not inserted into the end grain, so we're okay there. We decided that our moisture content is less than 19% for both in-service and fabrication, so we're okay there. We don't have any temperature condition. And our time effect factor, we do need to update this, right? We are going to be using the 1.2 dead plus 1.6 live combination, most likely will control. And our factor then will be from occupancy, so live load from occupancy, so it'll be 0.8. So we'll go ahead and toggle this to 0.8. All right. Okay, now we need to enter in our demand, and we said that we had 175 pounds of live load, of dead load, and 250 pounds of live load. All right, and it's showing us that we have a DC ratio of 0.85, so we are good. So let's go ahead and jump through the calculation here and take a look at some of the different things that that CalcBook is going to show us. So first we have just our load combinations, right? LC2A, so the 1.2 dead plus 1.6 live. And then we get into the capacity. And we have quite a few things here that we need to calculate. So we need to do some sort of preliminary design calculations. So our dowel bearing length in the main member is just the thickness of 1.5 inches. Same with the side member is 1.5 inches. And then we need to calculate our dowel bearing strength, right, which is based on our specific gravity of the member. So we get 5,600 psi for both the main and the side because they're the same. Then we have a ratio of the main to side. So since they're the same, it's a 1. Same with this RT value is a 1. Then we have some different values that we need to calculate that are going to eventually go into our yield equations. So we have this long K1 equation, K2, and K3. And then we have some different reduction factors for the yields modes. So we have several different yield modes based on the type of failure for this connection. So we have some different calculations that we need to run for this reduction factor RD, which will go into our yield modes. So once we've got those calculated, right, we can go into our yield mode capacities. So these are all our reference design values, lateral design values for the different yield modes. So we have yield mode 1 of the main, 1 of the side, and then yield mode 2, 3 of the main, 3 of the side, and then yield mode 4. And we would have some other ones if we were in double shear, but this is all in single shear. Then we can go to our adjustment factors. Right, our moisture content is less than 19%, so we have that as a 1. Our temperature is also a 1. Our group action, right, we don't have that for a single fastener, so that's also just a 1. We do have some interpolation to calculate for our end distance factor, that's C delta. We have one for 0.5 and one for 1, and we're sort of in between those, so we just take a ratio of what our end distance is, and we get a factor of 0.69. And then the same thing for the end or the side member. Our end grain, right, does not apply because we are not in the end grain, so that's a 1. Not a diaphragm, so that's also a 1, and then our toenail is also a 1. So lastly, we can just put that all together and get our LRFD design adjusted lateral strength, which is going to give us 715 pounds. And so our DC value is going to be 610 over 715, which gives us a ratio of 0.85. So that is a single fastener lateral load design in CalcBook. We hope you enjoyed the video. If you have suggestions or questions on the video, please let us know in the comments below, and we'll see you next time.